Have you ever wondered how we predict what a tiny quantum particle will do when we look at it? It is not like flipping a coin where it is always 50-50. In the quantum world, it is far more nuanced, especially when we consider something like a qubit. Yes, the theta angle, also known as the polar angle, on the Bloch sphere, absolutely determines a qubit's measurement probability. It is one of the most fundamental parameters in describing a qubit state and predicting its behavior. The reason for this lies in how we representing a qubit. Imagine a sphere called the Bloch sphere. Any possible state of a single qubit can be mapped to a point on its surface. This point is defined by two angles, theta, the polar angle, and phi, the azimuthal angle. Theta measures the angle from the positive z-axis, pointing downwards towards the xy plane. The closer the qubit state vector is to the north pole, which represents the zero state, the higher the probability of measuring it as zero. Conversely, the closer it is to the south pole, representing the one state, the higher the probability of measuring one. Specifically, the probability of measuring a qubit in the zero state is given by the cosine squared of half the theta angle. And, predictably, the probability of measuring it in the one state is the sine squared of half the theta angle. These two probabilities always add up to 100%, as they must. By knowing the theta angle, you can precisely calculate these measurement odds, which is critical for understanding and designing quantum operations. This means that by manipulating the theta angle through quantum gates, we are directly controlling the probabilistic outcomes of our measurements. For instance, a qubit perfectly in a superposition, sitting on the equator of the Bloch sphere, will have a theta angle of 90 degrees. This results in an equal 50% chance of measuring either 0 or 1, because the cosine squared of 45 degrees and the sine squared of 45 degrees are both 1/2. The phi angle, on the other hand, describes the phase of the qubit, which is crucial for interference effects but does not directly affect the probabilities of measuring 0 or 1 in the standard computational basis. So, the theta angle is not just a mathematical coordinate. It is the direct link between a qubit's geometric representation and its observable reality. Mastering the control over this angle allows quantum engineers to choreograph the probabilities of quantum outcomes, forming the very foundation of how quantum algorithms achieve their power. Understanding this relationship is key to harnessing the quantum realm's inherent probabilistic nature for advanced computations.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.